So what we're looking at here is that we're looking at some spiral growth and how Fibonacci's numbers and the golden ratio work out in nature, and how to use these in different ways. Okay, so this is what we're going to be looking at. This covers the first half. There's going to be a second video that covers the second half, going over gnomons and other things in the same spiral growth pattern. So the first thing is, so Fibonacci's numbers, or Fibonacci's sequence, I'm sure everybody has heard that. You've heard it some way or another. You've probably heard it in your Algebra 1 class, maybe even sooner. And what Fibonacci's numbers are is that they occurred when Fibonacci, who was around in the 1200s, I was thinking probably more Newton, 1600s, but Fibonacci was around the 1200s, and he was huge with bringing the Arabic numbers into the Western Europe, because at the time Western Europe wasn't using a very nice number system. It was like Roman numerals, and Fibonacci came along, and the numbers that we use now are actually the Arabic numbers. And he was the one that introduced that, and then math kind of exploded in that region because of it was an easy way of doing it. And so Fibonacci, in his book that kind of brings everything together and kind of did help do this explosion, Liber Bassi, I think. I don't speak Latin, so I'm not 100% sure if that's how you pronounce it. But he comes up with this problem with some rabbits. So basically the idea is that if you have two rabbits and you put them in a room, it takes them a month before they can reproduce. And when they reproduce, they reproduce a pair of rabbits. And then the question is, if the new pair, it takes them a month before they can reproduce, after X number of months, after a certain number of months, how many pairs of rabbits will be in this room? And that's what he's asking. And what he comes up with is something that's very simple but still very beautiful in what it is, and that's his sequence, or his series. And the sequence is just 1, 1, 2, 3, 5, 8, 13, and it's very simple to come up with what he did. All you have to do is just, after you start with your seeds, 1, 1 are called your seeds, or your starting. It uses a recursive rule, which means that you use the numbers that are previous to get the next number. And all Fibonacci's is that we add the two numbers previous to get the next number. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 5 is 13. And it keeps going. And that's all Fibonacci sequence is. And it keeps getting larger and larger and larger. But the thing is that just by these numbers, a lot of things have occurred from these that we've discovered. Now to find, let's say we want to find a Fibonacci's number. So if we want to find the 7th number of Fibonacci sequence, what you'd have to do is you have to find the 6th and the 5th and add them together. Well, the 6th is, so it would be f sub 6 and f sub 5. Add them together, so that would be 8 plus 5. So the 7th number is 13. And that's how you would do this. Now, if you come up with a problem like what is the 300th Fibonacci's number, which will take a long time for you to try to add all those numbers up and get there. So what happened is Fibonacci actually discovered or formulated a formula to find any of these numbers. Now, that formula was lost for a couple hundred years, I believe maybe even 100 years, and then a man called Jacques Bennett rediscovered it, and now the formula is named after him. Okay, and so Bennett's formula is this right here: 1 over square root 5 times 1 plus square root 5 over 2 to the n minus 1 minus square root 5 over 2 to the n. So if we want to find the 300th Fibonacci number, wherever there's an n, we write 300. So we take each of these to the 300th power. Okay. And what happens is that we come up with the number. It's pretty amazing that this formula, you think with all these square roots floating around, that it comes up with the number. But it does. Now again, when you're working this formula, please take your time, okay? Try to get as many exact numbers as possible. Don't try to plug this whole thing into your calculator at once. You might forget a parenthesis and it'll throw off the whole problem. So please take your time with this. All you have to do is just plug in 300 and you're good, and you'll get the 300th Fibonacci number. If you want to get the 200th, you just plug in 200 in for n, so on and so forth. But this is a nice formula to find any number of the Fibonacci numbers. All right, now the Fibonacci sequence, the Fibonacci number is very unique because all over we see and we've discovered it in different things. Now here's an example of a pine cone right here, and then I think that's a daisy. I'm not great with flowers, but I think it's a daisy. And what we see here is that our spirals in this pine cone going clockwise, we come up with 8 spirals, which is a Fibonacci number. Now if we were to go the other way, all right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, we see we have 13 spirals going the other way. Well, 13 is another Fibonacci number. And we see this in pineapples, we see this in flowers. Like here in the center of a flower, we've got 34 going one direction in the clockwise direction, which is a Fibonacci number. And the number previous to 34 is 21, which is going in the counterclockwise direction. If you look at petals on some flowers, they always occur in some sort of Fibonacci number. Now the reason for this is a combination between evolution and kind of luck. And it doesn't occur with all of them, but what biologists and other people have theorized is that it's the best way for a flower or a plant to grow. It's the optimal way for it to grow, to get the most sunlight and to do the best for the plant. And that's why that it occurs with these Fibonacci numbers. All right, not all plants do this. There's also something called a Lucas number, which is the same type of sequence. It's just a little different. The numbers are slightly off. And then some plants follow those. But a majority of plants that do follow some sort of pattern follow the Fibonacci numbers, which is pretty astonishing when you think of the randomness in this world, that these things in nature follow along in this Fibonacci number and this golden ratio. Now the golden ratio is derived from the Fibonacci number. The golden ratio, or phi, this Greek letter here is called phi, and that's the notation or the symbol that we use for the golden ratio, comes from the Fibonacci number. As Fibonacci numbers get larger, if you take a Fibonacci number, 55, the 10th Fibonacci number, and you divide it by the one previous, the 9th Fibonacci number, 34, you get the decimal 1.61764. Now if you keep getting larger and larger, what you see here is that you see that these numbers are getting closer and closer to a single number. They keep jumping. One's larger, smaller, larger, smaller, larger, smaller, larger, smaller, and they keep kind of oscillating between some number. Well, as you get bigger, they have found that it comes up to about this number, 1.618, but it's an irrational number that goes off into infinity. There's actually more digits to this. It never ends. And the exact number of the golden ratio is 1 plus square root 5 over 2. That is the exact golden ratio number. And that is derived by using the quadratic formula and setting up the problem of what the golden ratio is, which is like 1 plus 1 minus x. And but that is what the golden ratio is. Okay? And it always occurs. And a lot of people have said it's the most beautiful ratio. That's questionable, but it's something that has occurred from the Fibonacci number. Okay. Now that's the end of the first 3 sections. After this, we'll go on into talking about gnomons and spiral growth in nature. Okay, so that'll be the next one. We'll cover those last 2 things.